for having you wait here a little bit. Now is actually the best time to be here because I don't know if you looked outside, but it's really raining. So now you're stuck with us until the end of the day. After lunch, we chose a very interesting subject for a talk about something that touched almost everybody. It was a huge CrowdStrike event that gave the internet a blue screen, and that doesn't happen very often. Since then, of course, it did twice to other companies. So we have Gal to tell us about that. Gal is a senior cybersecurity and software architect at Intel with more than 25 years spanning kernel development, embedded systems, and security across platforms and operating systems, bringing deep architectural expertise to dissect what really happened with CrowdStrike and what defenders can actually learn from it. Gal, welcome.
Thanks, Inbar, and thanks everyone for joining me after your lunch. And I will try to give you a nice dessert with this talk about CrowdStrike and this cyber attack, the biggest one that never happened. And the only problem with me giving you dessert here is that this talk is supposed to kind of inspire a little panic for you. Well, that's, of course, if you haven't brought your towel with you. Anyone brought their towel with them? If not, I can offer merchandise later. But if you want to enjoy this, then try not to panic. And if you're thinking that you heard about Cloudflare and why is he talking about CrowdStrike, then don't worry. We'll also talk about Cloudflare as part of this. So, kind of, Inbar already introduced me. I think I've had a chance over the years, given my background, to do black hatting and white hatting and software product development. And I have a passion for software architecture and its aesthetics. And I have a passion for baking in cybersecurity very early in the product development life cycle. And when I looked at this, it kind of resonated with me, and I hope it will resonate with you, and hopefully not create too much panic. So one thing that's very important when we're thinking about this lecture, it's really not about CrowdStrike, and it's really not about Cloudflare. They're just ones providing us with case studies, and you can call it cautionary tales. And they're giving us a very rare opportunity for a look into the post-mortem processes within large-scale development organizations. And the point is, and that's really what I want you to take from this, is that the events that happened here and their conclusions are not specific to these companies. They could have happened in any large-scale software or hardware development company, or really any company that deploys software widely, and the conclusions are much the same. So, let's see, what do we have here? So, what happened? So let's start with CrowdStrike, right? And CrowdStrike on July 19th, 2024, a Friday, mind you, they decided it was a good idea to push a software update to a software of theirs called Falcon, that resides on Windows OS-based end-user machines, and it tries to detect cyber threats and mitigate them. And, well, they pushed the update. And then all of that happened, basically. They crashed 8.5 million PCs into a blue screen, and not only a blue screen, but a persistent blue screen that continued forever. And it started with billboards in Times Square. It continued into canceled operations in hospitals, banks, border crossings, courts, and thousands of canceled flights. The economic impact was huge. Just in Fortune 500 companies, we're talking about roughly $5 billion of damage. In the UK economy, it was estimated in £2 billion. So, kind of a small thing. if you look at the timeline of all of this, it started on roughly at 4 a.m. Greenwich Mean Time, and when CrowdStrike decided to release that file with that update to those machines all over the place. And within, as I said, a few minutes, they got the update, they processed the update, and they crashed. And they stayed crashed, as I mentioned. So, and it needs to be said in their favor that within 90 minutes, CrowdStrike already understood where the issue was. They reverted the problematic file. They released a fixed file, which didn't really help much all those blue-screened machines, right? And in general, kind of the industry went into mayhem for several hours. It took roughly 12 hours for CISA, the US cyber organization, to officially declare that this was not a cybersecurity attack. It took CrowdStrike 36 hours, roughly, to actually publish a full manual of what to do, and we'll talk about that a little more in a second. And Microsoft tried to help in the next day with a Windows PE release that was tuned for the recovery effort. But in general, things took about 10 days before CrowdStrike actually could declare that 99% of their customer base actually came back online. So it was a big deal. Along the way, the US government, the US Transportation Department started an investigation with all the flights. And by September, CrowdStrike was invited to the US Congress. So a small, big deal. It's a nice anecdote that in terms of the financial experts look at this, in the first minutes, there were a lot of predictions that this won't have any effect on the global economy. The CEO of CrowdStrike kind of knew different already in those several minutes because he already started the public apologies. He kind of knew where his stock is going. But again, in their favor, it should be said that they were able to resurrect their investor confidence, and that's not something trivial given what occurred. So it was a big deal, and for those unfortunate IT guys that needed to handle this, so they kind of realized they were in trouble, kind of on fire, so they waited patiently for CrowdStrike to release the instructions, and they got a kind of a book with, these are just the names of the chapters in that book, with all the different permutations of how you have to deal with this issue. And they kind of understood that, well, they'll have manual, tedious, on-prem activity to do, basically going to each and every machine and taking care of it. And I'll say this is the only little point in the talk where I have this pride in my own organization, in Intel. And the small thing here is that small people that bought Intel vPro platforms, well, they had it better because if they had their active management technology running on the little subprocessor that runs in those platforms beneath the OS and works even if the OS does not, well, all they had to do was remotely connect to those machines, reboot them, open a command line, change the file, and that's it. So they were done within a few minutes, unlike all those other poor bastards. So that's a small point about Intel. And that, by the way, helped a lot of organizations, and today is helping Intel sell a lot of vPro platforms. But more importantly, let's get back to our thing here. So CrowdStrike, what happened there? The CrowdStrike Falcon sensor is based on an AI model that is used to detect the threats. And CrowdStrike, they update that through a collection of data from all their sensor network and through human intelligence. And then at that point, they push updates from their cloud back to the sensor in the form of what's called channel files. And those channel files get into an interpreter that's based on regular expression handling. And it uses a template file to define the structure, the legitimate structure of the data in those files. So what happened, or more precisely, when happened? So it actually didn't start on July. It actually started way back in February with a release of a new version of the sensor that included a new template file that had 21 input parameters within it instead of the original 20. And it had a wildcard, actually, in that release that allowed to disregard that 21st parameter. And all was fine until that Friday. And then CrowdStrike released their new update. I'm sure you can guess what was that little update by now. They created a template that enforced the 21st parameter. And that's all fine. So the content interpreter went ahead and read the 21st parameter. The only problem was that the code of the interpreter was not updated for 21 parameters, and it did an out-of-bounds read, the simplest cyber bug that we know, right? Only if it happens in kernel, right? So in Windows, you get a blue screen. And if it's a driver that comes up on each boot, that's a persistent blue screen. So all fun for everyone. But how did this happen? How did it pass the integration test and the release test and the stress tests? How did it pass the initial deployments which CrowdStrike have claimed they did? So again, CrowdStrike did a really deep dive into trying and finding where were the problems. And their reports and Microsoft reports, because they pulled in Microsoft to help with this, are very interesting, and I encourage you to actually go and read the originals, but I'll digest things here for you. So it started with understanding they missed some compile time checkers. Basically, they generated files, and without actually checking that their assumptions about the consumer software, how it's written, they're not checked at the source, right? So they could have basically stopped the whole thing before deployment if they had this, so they added those checkers. They still understood it's also something that they need to do on the consumer software, so they need to add input validation code. And they added input validation code to check, the boundaries of that array that they were reading. And then from that, actually, they understood it's not a discrete event with that specific line of code, and they went into a more full-fledged secure code audit from that point on. And then they looked at the testing, and again, they saw things that were familiar. All the testing was of positive flows and of hard-coded content. They had 12 test cases, and they used channel files and template files that were manually authored and were not updated when the actual code was updated. And they also saw that there was no test actually checking input validation code in any way. So they added negative testing, and they added fuzz testing, first for the template files and channel files parsing, and later for more interfaces, because they kind of created a roadmap of fuzzing. And it was not the only conclusions. They had a couple more. One was around the deployment. They understood they needed a staged deployment with more control, even more awareness for the customers, even some control of the customers to allow them to time things. And they understood that there are some software architecture conclusions, again, kind of related to cybersecurity. The first of which was, let's move activity from kernel to user space. Should be very familiar here, right? Least privilege and all. So you can see there the new partition they did for that specific software. Of course, they moved the parsing of files coming from the net to user space, and then the conclusions can go to the kernel. And Microsoft used that opportunity to push their UMDF architectural driver model, and that's a very good thing. Intel, by the way, is also working with them on that. And they also pushed memory-safe languages, and not only them, since then CISA and others have continued to push this, and of course Google has been pushing this for a long time. And Rust, of course, is the classic candidate for kernel. I was really hoping to tell you about Safe C++, which was an initiative that was really picking up in the last year with some extensions, but unfortunately the standards body of C++ rejected that in the last couple of months. So we're back to Rust as the main candidate, and hopefully something will come up for C++. But it doesn't mean you can't solve the issues in C++ at all. Okay, so I think you all saw, being cybersecurity people, that if we had only followed cybersecurity best practices, even one out of all that we've seen, we could have averted that catastrophe, right? So we wanted the cybersecurity best practices from the get-go. And okay, we saw it for CrowdStrike, but let's look at another example, a completely different example. Well, maybe not a completely different example. Cloudflare is a completely different company. It's a content delivery network, a CDN provider, and it basically spreads servers in the geos of the consumers so that when they ask for the websites, they get better performance, better resiliency, they get some protection against distributed denial of service attacks and other security threats. So it's a very different company in what they do. But again, they needed to send out an update of their software. Fortunately, they didn't on Tuesday, or not so fortunately. This time for something called the bot management system, which is something running on their servers. It's not going to the end user machines. And they broke the internet. They broke the internet. Basically, they blocked access to endless amounts of websites, big and small, starting from ChatGPT and Twitter and going to League of Legends and the New Jersey Transit system. And it was all fun, and they, of course, apologized a lot and, again, looked deeply, and they really did, into what happened there. And you can see, by the way, how the internet was blocked for those several hours. It actually took about 3 hours and 20 minutes for this to be mitigated. Even 3 hours came up to around $250 million in economic impact. The only problem was that it happened again, just last week. And this time on a Friday. And just a different server. This time it was their web firewall, and they pushed an update to that one, and they again broke the internet. Luckily, this time, just for 25 minutes, so they kind of improved in their speed. But the amount of apologies increased, and so did the discussion of the fragility of our internet infrastructure and the dependency on several large infrastructure providers. And I'm sure this will continue to pick up, and it will be a very interesting discussion. But let's focus for now on what happened in those last couple of times. So in the first time, we talked about an update to the bot management system. And just like in the CrowdStrike case, it's a cyber detection mechanism that's based on AI models and tries to monitor bot activity on the net and see malicious bot activity and prevent those bots from accessing those websites via the CDN. And they continuously update this data, and they send out the updates to the servers via a feature file, not the channel files, like in the case of CrowdStrike, completely different. But this time, they do it very rapidly, every 5 minutes. These files are generated from queries into an internal database that Cloudflare has. And what happened actually here is a combination of two things. Their IT guys, they did something very nice. They actually relaxed the permissions on that internal database for the sake of internal users and applications. But that coincided with the fact that this query for the bot system, it was permissive. It was not exact. And so once the permissions were relaxed, it kind of pulled in a lot more information than it needed. So luckily, they didn't have any leak of security secrets or privacy items, but they still wound up with a feature file that was roughly double the size of what it should have been. And as their CEO said, it that larger than expected file actually found its way immediately to all those servers. So when it did, luckily, the software there on the servers, it actually had a check. It identified the fact that the file was in the wrong size. However, it just decided to panic and disable the service. So we didn't get code execution or another crash, but we still disabled the service. And let's look at the other example. Again, they sent an update, this time of a file with the updates to the rule set of the firewall. They did a very small thing. They just disabled a single rule. But the code that parses the rules had a small line that did execute on an object of a rule, and it kind of assumed that it would not be null. But nobody checked that it's not null, and it was not written in any memory-safe language, and so that server crashed. And as, again, the CO said, this was a straightforward bug that was there for many years, nothing new. And Cloudflare, they kind of tried to build on the fact that they actually had already a new version of that server implemented in Rust. They just didn't get to deploy it. So actually, kudos to them for actually moving in that direction. I'm not sure that means they should have had this originally, right? Because we can solve this without Rust, right? And in the end, you can see in their conclusion, the summary of their conclusions. So they talked about hardening the ingestion of their files. So not just of external files coming from untrusted sources, but of their own internal files. And that basically makes sense when you're talking about mission-critical systems like that, right? They're very sensitive. And they'll enhance their rollout and deployment mechanisms. Again, like CrowdStrike. In their case, they also had this thing about streamlining their break glass capability. Basically, they're talking about the methodologies and tools that are used in emergency recovery to actually adopt them and test them and see that they'll actually work when you need them and work fast. They'll also look at the design. So they'll review the failure modes and the error conditions and the patterns that you all probably know well. For mission-critical systems, they'll adopt a fail-safe, fail-open approach wherever possible and only leave the fail-secure approach to those places that really, really must have it. And so those systems will default to operating rather than being disabled. And they found on the periphery some additional issues. For example, that the systems for log compilation and for collecting core dumps, they were stressed and overwhelmed when the actual event happened. And they were not originally stress tested for something like this. And when they actually had to recover, they didn't just need to recover the main system, they also had to recover these systems. So it prolonged the time of the full recovery. So they were looking into this as well. I think a couple more things that should be said here is that just like in the CrowdStrike case, they could have looked at the input validation assumptions at the source, right? And not deployed the files. The CO talked about it. And in terms of the memory languages, okay, they are very important, but they don't eliminate the need for a good design. I mean, the second incident, maybe Rust would have done it if it was deployed on time. But in this first incident, the code was actually in Rust. But it still panicked. It still disabled the service. So again, you need to be careful in your design. Look at the business objectives and the security objectives when you do it. And again, we come to the same basic conclusion that if we had followed cybersecurity best practices from the get-go, we would have saved us from that catastrophe, or couple of catastrophes. So very different, but very similar. And if we kind of try to wrap it up into takeaways, and for a very large audience of roles in the organization, So the first thing is you can use these examples as great training material within your organizations, or if you're providing mentoring to other organizations, use these. These are great. From the cybersecurity perspective, they exemplify how malware that's been widely distributed can cause a lot of harm. Supply chain attacks can be very effective. It was seen here very nicely. But real malware, it won't stop necessarily with the OS. It can do much worse things, right? It can try to inject code, to leak information, and it can actually try and hamper any attempts at recovery. So a lot of work here to do, and of course, the IT organizations, they really should adopt as fast as possible better recovery mechanisms and tools for their OSs, for platforms, for servers. Product software organizations, they need to employ stage deployment. This is essential. And it still boils down to that fact that cybersecurity best practices, they are good. They're not just good for protecting us from cyber attacks. They actually work against ordinary bugs. They improve our resiliency from threat modeling to fuzz testing. It's all critical. And if you sum it up with AI, of course, so AI can help you very much, with coding best practices, with test coverage, with better and smarter recovery mechanisms. And those are the good things of AI. And the last thing is that AI can do also the harm, right? We're putting so much new AI-generated code into production-grade systems, into the product code, DevOps code, test code, that just like the regular cybersecurity best practices, now we need actually to adopt the security for AI and AI for security mechanisms and methodologies to help us with this, but not just for cyber attack protection, but just to make our software more resilient and just to handle the ordinary bugs. So I hope it was interesting, and I hope you enjoyed it. And I'm leaving you with a list of links if you want to delve deeper into any of the subjects that I've mentioned, and my contact details if anyone wants to ask more questions or give feedback. And thank you.